Hey students, welcome back to chemistry. We're going to talk about section 4.2 today. We're going to pick up where we left off with different models of the atom. So we're going to talk a little bit beyond what Dalton talked about. Dalton's understanding left us off that matter was made of individual atoms or small balls that were distinct from each other. So that was the breakthrough there. There was significant breakthrough in the late 19th century. In understanding what is called the nuclear atom, meaning that there were subatomic particles. So this idea of cathode ray tubes in computer monitors, old equipment, when you think of old TVs and old computer equipment, even old amplifiers for electrical instruments, or use what are called tubes or cathode ray tubes. And so that was rather common coming out of the science field and into the more the consumer field. But this is how those cathode ray tubes help discover what are our three subatomic particles, which are protons, electrons, and neutrons, which you may have been familiar with before. We're going to talk in detail here. So the electron was discovered in 1897 by J.J. Thomson. He discovered it by using, noticing the behavior of a particular type of particle when it was in a charged environment. So Thomson performed experiments that involved passing a gas, electrically current through a gas at very low pressure. And so this was the result. So he had a battery or some sort of source of voltage of electricity that would go through this tube that had a gas in it. So there's a gas inside of here at a very low pressure. And he had two metal discs that were conducting the electricity. And then a vacuum was placed on that to put it at a low pressure. By applying a vacuum, it lowered the pressure of the entire system. And this is the cathode ray tube right here. So when that was put into place, and here's a picture of it. Here's the two wires running the current, the positive and the negative ends there. And then when a magnet was placed on the cathode ray tube, the flow of particles or the flow of the gas seemed to go towards one side, or it went up towards that side of the magnet. It was deflected, as the slide says here, that meaning that that particle or those whatever they were moving by were charged. So he did another one, set up another experiment where he had a positive plate, a positively charged plate, and a negatively charged plate. And as the current went through here, through the cathode ray tube, through a slit, he noticed that the stream of gas would flow upwards towards the positive plate. And so, since opposites attract, if this is positive, whatever this was negative. So he called that an electron because it was electrically induced here by this voltage current. So that was his discovery of the electron, was a negatively charged particle. We'll learn later that it's not really a particle, but for now we can call it a particle. So he concluded that a cathode ray tube is a stream of electrons, and are parts of all elements. Now we're going to talk about the discovery of protons and neutrons. First, protons. In 1866, Eugen Goldstein observed similar to a cathode ray tube. He used that as well. Found rays flowing in the opposite direction. He concluded that if they're flowing in the opposite direction rather than towards the negatively charged plate, so going back to here, imagine that the stream is going towards the negatively charged, kind of scooping down this way. That means they must have a positive charge since they're moving towards the negatively charged plate. So he called those protons, positively charged particles. He called those protons. So they understood the existence of protons and electrons. Now you notice here we have 1886, and then we have 1897. So we're looking at the late 19th century, and it was in 1932, some 30 to 40 years later, that a physicist named James Chadwick confirmed, and notice this word, confirmed the existence of yet another subatomic particle called the neutron. Now, the neutron was thought to exist because if you have positively charged particles together in a nucleus, they're going to push their way apart. So they thought there might be some sort of spacer in there that was keeping the positively charged particles from literally blowing out the atom. So the neutron was actually discovered as a subatomic particle that has no charge. It has no charge. So the proton is positive, electron is negative, and the neutron has no charge. So here's a little table that shows that. These are the symbols I'll be using in class and in these presentations. Electron with a negative symbol, proton with a positive, and N with a zero symbol next to it, or a superscript. And these are its relative charges. Now, the masses of each, these masses are considered, when we talk about masses of atoms, we only consider the proton and the neutron because the electron's mass is so small in relative terms here. If we just had one as the mass of a proton and a neutron each, the mass of an electron would be 1 divided by 1840. So it's very slight and very negligible that it doesn't need to be considered when considering the mass of an atom. So let's talk about the atomic nucleus. How can you describe the structure of the atom? Well, J.J. Thomson again, he came to feel what a positive materials, electrons were distributed throughout. So this idea is that they thought that the almost the plum pudding was called the plum pudding model. That J.J. Thomson thought that they were evenly distributed throughout the entire thing, much like Jello may have gelatin spread throughout. This was the idea that Thomson had. This model turned to be short-lived because of the work of the next scientist we're going to learn about is Rutherford, Ernest Rutherford. Ernest Rutherford was a New Zealander, and he worked with other physicists in Manchester, England, and directed what's now called the alpha particle gold foil experiment. So what these scientists did is they projected or shot alpha particles. We'll learn about alpha particles later in here, but just know that they're small radiation pieces of radiation off of every atom, and alpha particles would flow through this gold foil. I want you to think of aluminum foil that you might use to cover up some food. This gold foil is like that, but it's gold. And so what and around here was this fluorescent screen that would pick up the alpha particles, tell us where the alpha particles went. Whenever did they pass through the gold foil? Did it get deflected in some way? Did it get refracted? So this is what happened when the alpha particles, some of them went through, some of them were deflected to the side, and some of them were completely bounced back. So this is where they were detected on the fluorescent screen right here. This is where they were detected. So he concluded that there must be something going on here. There must be something in there that is not allowing the beam to go straight through. Some of them do, one does, but several other ones get deflected. Why is that occurring? So what he came up with is that there are little balls, nuclei, in here. So this is all the gold foil here and the millions upon millions of gold atoms that make up the gold foil. What happens is that the alpha particles may hit a portion of the nucleus and deflect off. Some may go straight all the way through and go to the other side. Others may hit this in such a way that it bounces back, much like a cue ball would hit an 8 ball in pool or something like that, right? So this is what they'd explained, that most of an atom. So this is what he concluded from this experiment. Most of the atom is empty space. In the center or near the center is a nucleus that that each atom contains a nucleus. So that's where the nucleus came. Here is the tiny central core of an atom. It is composed of protons and neutrons. So it's concluded that the protons and the neutrons live in the nucleus of the atom. All right, so the nuclear atom, the protons, electrons are located in the nucleus, and electrons are distributed around the atom. We'll talk about different ways of how the distribution of electrons have been seen over the years, and how they're currently understood in what's called the quantum model. So we'll talk about those in our next time together. So thanks so much for listening. I hope this is helpful for you. Bye-bye.